First of all, I would like to thank the organizers for the kind invitation to give this lecture, and a colleague for presenting me. As you can see here, I'm with the Faculty of Chemistry and Center of Chemistry. This is somewhat unusual in our country. Within the faculty, there is the chemical faculty, Faculty of Chemistry, and the Center for Chemistry, sharing instruments. I'm pointing this out because we will be talking about instruments here on which these analyses are done. Various analyses are conducted. So within the Faculty of Chemistry and the Center for Chemistry, there is a Center for Instrumental Analysis. As you can see here, its acronym is CIA. It's clear that this is something that we always use acronyms these days. So it's an acronym for the Central Intelligence Agency. So this is what our department does whenever. So we try to discover unwanted things in certain compounds, when compounds are not pure, when the reactions are not as desired. I will talk about an analysis that is very complicated and difficult here, analysis of drugs and metabolites in biological matrix. The first question that is asked is how a drug is absorbed, what happens to it, how it is metabolized and eliminated by the body. One of the best responses that we can give is that we do an analysis of bodily fluids, and not only fluids, but also different tissues. But as I said, this analysis is very complex and difficult because it is clear that the material, these analyses that are done, we have very little sample and analysis has to be done quickly. The drug is quickly absorbed. Metabolites are often unstable and there are different matters. I will not talk about metabolitic paths. You're probably more familiar with them than I am. I will mostly talk about the analytical aspect. So what are the most frequently analyzed samples? This is urine, blood, plasma, tissues, feces. But the key thing for this lecture is that substances that are established are in the sample in extremely low concentration. In order to catch a metabolite or parent compound, we must eliminate all the distracting substances, and we have very little, small quantity of the compound we are looking for. And the most important thing here is that the detectors or the analytics that is applied must be very sensitive, and we have to have very sensitive detectors. It is impossible to do such analyses without the so-called coupled techniques, or so-called hyphenated techniques. The techniques that are used for them are mass spectrometry, that is the leading technique in the work with such samples, and it is most widely used. So in the cases when we cannot get all the answers from the mass spectrometry, we also use nuclear magnetic resonance. Why couple techniques? It's clear that we cannot put one sample directly into MS or NMR device. We have to purify it first and then to eliminate all the compounds in it. And this is usually done with liquid chromatography. Liquid chromatography can be of different types. So we have high efficiency liquid chromatography that is one of the most usual ones, and we will explain how this is coupled. In the event of MS, it usually gives the answers that are fairly satisfactory to all these questions, but in the event of something unexpected happening with the drug, if it is not possible to determine the position of oxidative change because we have isomers that cannot be determined by MS, or a metabolite is there that is of unusual structure, in such an event we must use NMR, and then we have a combination of LC and NMR spectroscopy. In this lecture, I will mostly speak about the application of combined methods, coupled methods. I will use several examples of drugs to explain what is really done in these analyses. I will try not to burden you with too much information, but what is used in these coupled methods when we have LC-MC, LC-MS-MS, and LC-NMR. Before that, we always have to use solid phase extraction before such a sample is taken, for example, plasma or urine. We have to do SPL analysis. I would like to remind you about chromatographic methods, methods of separation. You probably know and you have used them in some occasions. There is gas chromatography, liquid chromatography that can be high performance, LC, TLC, and with these chromatographies we combine GCMS, infrared, and UV. They can be combined with all the chromatographies. In determining, establishing these drugs and metabolites in biological matrix, we have to use combinations of mostly LC and MC, LC, MC, MC, MS, sorry, LC, MSN, and LC, MNR. GC was, gas chromatography was initially used, but it requires thermostable and evaporable samples that are quite rare under such conditions, and we have to derive them, and this used to be used, but these days almost always we use liquid chromatography. I will briefly tell you, if you're not so familiar with solid phase extraction, I will just briefly explain. If we have a sample, a biological sample, tissue or plasma or anything else, it is usually in the aqueous solution, and what we are looking for in such material, we look for a drug that has either changed or not, and the metabolite. We have to purify it somehow, eliminate proteins, salts, and disruptive materials, and this analysis, since we have to do a lot of analyses. First, they pass through a cartridge that can be a racing or 18 columns can be different. It passes through the cartridge, and then so this is the cartridge, and this red here, the sample is there, and the solvent passes through it. And the next stage, we had the aqueous solution, and we take from the cartridge, we add a solvent, and we remove different compounds of different polarity, and we concentrate the sample, make the sample more concentrated. We have to do it because we are talking about very small quantities of the substances we are looking for, and no device is sensitive enough to be able directly to do something from the plasma, urine, or blood. I have to say a few things. I don't know how familiar you are with this. I would like to say a word. Since the main method that we talk about is the mass spectrometry, I have to remind you, we all know what molecular weight is. But how to measure molecular weight, how to go down to the level of molecules, to mark them and measure them. We have scales here. Obviously, we cannot use scales, but how can we get to the molecular weight? We can do this through the mass spectrometer. It's a device that determines molecular weight, and it is the only device that can actually precisely determine it. It can also provide us with information about the structure of compounds. There's great importance of the structure of metabolites, how this drug was transformed, what happened to it. So we need this and what it can do. So it can identify, do a quantitative analysis of metabolites, proteins, drug candidates, peptides, all different types of organic substances. Today there isn't any material that cannot, whose molecular weight cannot be determined. This is not quite so simple as we might think. So we can determine molecular weight for this material with which the table is coated, but the thing is how to get this into the instrument, how to do it. Let me remind you that all elements are defined, identified by their mass. We have accepted this. There are masses, fine, so what? But the mass, so the molecular weight is 150, 500, 600, but can mass be a round number? It cannot. Let's see why. The elements, most elements have their isotopes, and we measure a mass relative to the carbon that was assigned 12. The agreement is that the carbon has mass of 12 and everything else is measured in relation to it, but even the carbon has C13 atom that is so it has 1.1 isotope, and the mass of C cannot be 12. So why do we care about this? Why am I saying all this? Who cares about the isotopes? The mass, as I said, is defined by round numbers, but this is not enough for us. It is not enough for us to say that a mass of something is 300, 400. In this awful mixture that with which I started my lecture, there are a whole lot of compounds in a very complicated mixture, so where's the metabolite or drug in this mixture with unprecise mass with 120 mass 120? We cannot possibly know this. Why? I already said that a mass is defined relative to carbon. Let's first of all see the isotopes of the most abundant atoms. There is HCNO. They all have isotopes and have certain abundance. And when we do their mass in any compound with the instrument that has high resolution, MS, we will get 4 decimals. And this is very important for this analysis, because this is the only way, when we define something with 4 decimals, can we determine its structure and to see which compound we are dealing with. Let me show this on this example. We have the first peak. This is high resolution MS. So when we have a mass of 28, we can find CON2 and C2H4. So, and then we say mass is 28. But when we have the good device and the so-called high-resolution MS, we can see 2799, 28, 2803. We have 3 compounds, CON2 and C2H4, that can be separated, differentiated. In a compound, you can imagine, in a mixture we have 50 compounds below 1 peak, and we cannot. But when we do it this way with 4 decimals, we can actually know which compound we are talking about. A little bit more about the MS. So we have to know what this is about. So the different compounds can be uniquely identified by their mass. Here we have only 1 decimal. Ethanol, small mass. So the mass can do 300,000 daltons. Here we have drugs never have such large masses, so they are relatively small masses. So the resolution of the so we always have to work with devices with very high resolution, and to make the smallest possible errors in determining the mass. So here we have the resolution that must exist in order to have 50 ppm error or 55 ppm error. Sometimes even 15 ppm is not enough. We have to go for much smaller error when you have very low concentrations and you want to determine this. I'm saying all this, for example, here we have a definition of picogram. Perhaps you know, or you have forgotten, picogram is the 12th part of the unit of the gram, 12. 10 to minus 12. And sensitivity quadruple LCMC is 0.1 picogram. But if we look at, if we see that EPA arsenic in drinking water can be up to 55 picograms per microliter, or cyanide 200 picograms in microliter, so you can see what the concentration is like. And it says here that one typically messy fingerprint that we can leave can have 20 trillion picograms. So imagine a device that can detect 1 picogram. It is very sensitive, but this can also be a big problem if you can detect everything in such small quantities. Then you have a big problem how to establish what you're interested in, and that's why analysis is difficult and devices are very sensitive. But this can make your life very complicated. This is a typical mass spectrum of aspirin, and this is done not with precise mass, but with somebody takes an aspirin or any drug and he's interested in the mass. This is the so-called molecular ion. These are fragments, and the ion was the molecule had to be ionized. We took away its electron, and it became an ion, and it becomes unstable and falls apart. How did it disintegrate? This is what we are interested in, because through this we get to this structure here, a small molecular ion, and this is important for the determination of the structure. And now the basic mass principle is we have to ionize the molecule. We have to make it either positive or negative ion, because without it we cannot measure its mass. So when it becomes positive or negative, it then goes into the analyzer, mass analyzer, and we get the spectrum that we had seen. And when it comes to the detector, you can see the spectrum. So the basic issue here is how can we do the ionization? This gentleman here in this picture does mass spectrometry, and he's thinking whether soft ionization or hard ionization should be an option. This is the basic issue in MS, how to hit this molecule. This vase is a molecule, whether this molecule will be hit with a lot of energy so that it will disintegrate completely, or we need to be more gentle. In both cases, in these cases, we get completely different. So he opted for a stone, and what did he get? He had a vase, and it's our molecule. He got thousands of fragments. And the issue here is what he will do with these fragments. From these fragments, we need to determine the structure. The method in which we ionize the molecule with great power, if it do it with great power, it falls apart into thousands of fragments, and it's difficult to get to the structure. Until 10 years ago approximately, it was not possible practically to do the soft ionization. We had to do this way, the hard way, because there were no technical solutions for this. And most spectrums that exist were done with the so-called, with the high power heat of the electrons, and we were happy to get to the molecular weight. But today, we do so-called soft ionizations, and it's more easy. You get more structural information. We have an example of an analysis here of gastric juices. It is done in a patient, for a patient that was for a long time taking percodan. He excessively used percodan, and here we can see all the components, molecular weight of the aspirin, caffeine, and all the components. And this is an analysis. We got all the molecular weights. This is a purified spectrum. We took out everything that we wanted, and so how was this obtained? It says here, it is done by the so-called chemical ionization, CIMS. This is one of the softer methods of ionization because we got nice molecular ions. When we do the analysis of drugs and metabolites, we always have to use the so-called soft ionization. So let me show you what it is. You have a slingshot, and we get 2 or 3 fragments at most, fragments of the Vajs molecule. Now I'd like to move on to a few examples and show how this can be analyzed with how certain drugs can be analyzed. Here we have a formula for diazepam. From the point of view of the MS, it has N and chlorine. If you remember, chlorine has 2 isotopes, 35 and 37, and they are very useful, and they can be defined with MS, with bromide as well, because they have 2 isotopes that have different mass by 2 units, and then it's very easy to recognize them in the MS. Here we have a liquid mass analysis of a rapid analysis for different. We have a list here of all the different types of benzodiazepine that have different chlorines, and we do this analysis. First we have, so when we do liquid chromatography, you probably know this, the basic detector is UV spectrometer. So first we get the UV spectra. From this we could see nothing. So then we have ion chromatogram of different compounds that are drugs in this case. So it's a swift analysis that can be done this way. And the key thing in this analysis is to have, we have different Cl atoms, and we know immediately where we are. Why am I saying this? Why is it fast? Rapid chromatography is important. Very frequently analysis have to be done fast and have to be correct. In a short period of time, results have to be obtained. One of the methods for such analysis to be done, if there is Cl in the molecule, and drugs often have Cl, so analysis can be done well and quickly through Cl. This was analysis only the liquid one, MS. First we do chromatography on solid phase extraction. If we are using a bodily fluid, then we do liquid and then mass spectrography. Sometimes it's not enough just to do HPSL, we need mass as well. So we need, it's not do it just once, but we have to do 2 mass spectrographies. Here we have the chromatogram from the when we put in a compound into the liquid, then we get this. This is not a great chromatogram, but that's how frequently what drug analysis often look like. It's a So then who knows what is hiding behind the peaks? And then we decided, so if we opt for this peak, how will we do the mass analysis? We want to see what the mass is from this peak. We do the first mass, and then this might give us something that we are not quite sure. We are not particularly confident that this is the right compound that we want, so we will do again one of the peaks from the mass. So we will do the mass again, and then we will be able to establish what originates from what. It's not enough just to have molecular weight. We don't know what part of this molecule originated from. So I would like to explain what we are. So very frequently we do MS, and metabolites usually cannot do without this. So we use 2 MS analyzers combined in one instrument to analyze analyte ion, and it is separated from the mixture, and then fragments are generated and then analyzed through MS again, and I will show you this in an example. I will show you how this works in an example in relatively simple for amphetamines in human saliva. This is a fairly simple example. So this is liquid MS. Amphetamines, as you know, are very frequently used. So this is the general formula. There are obviously different ones, but this is amphetamine. So it's a very simple molecule. But there are pills that are widely used. There are all sorts of combinations of these amphetamines. Ephedrine is the natural example, one that was first used in China. The Chinese knew about it and used it a long time ago. And now various amphetamines are used in the pills that are widely used in cafes. They can be bought very easily. Sometimes there is a need to do an analysis of amphetamines in saliva, and it can be done very quickly. They're all very similar compounds, and analysis can be quickly done with MS because they give similar fragments. This is how mass ion is done. So this is MS. This is ecstasy. How? So we have similar molecular weights. So now we want to know which ion is a mother and which one is a daughter. What originated from what? This is important for establishing the structure of something. So it looks simple, and you think, oh, this. This any combination of so what originated from what, until you do this analysis, you cannot determine the structure. So now this is a simple analysis. Iron 194 originated in iron 163. So we know we can decipher the structure from this. So this is what the MS analysis is used for, in order to determine the complete structure, to see which fragment belongs to what. Now I will use this example of buspirone to show you how a metabolite analysis can be done in bodily fluids. It's difficult to determine them, and metabolites. It's assumed. So if we have a drug first, and then it is usually transformed metabolically into a compound that is more hydrophilic. It usually has hydroxyl group and something else possibly as well, but so we assume that there are hydroxyl groups in certain places. So these are metabolites. We have mono and dihydroxy. And how will we determine these hydroxy groups? It's very important to determine this. Here we have part of the mass spectrum with different masses, precisely defined with 4 decimals. There are many masses. We can obviously go for these metabolites, target these metabolites, but so these are assumed metabolites with one hydroxy group, aromatic core. But this hydroxy group in this part here, we have to determine its position. This could possibly be established because fragmentation is such. You will see where this can be assumed based on the fragments. So we did an analysis with precise masses, and the fragments are determined on their basis. The position of this one hydroxy group was determined at the aromatic core, but what could not be determined on the basis of these precise masses is the location in this fragment, the location of the other OH group, and it's important to know the position in order to later be able to know the structure of the metabolite, because the fate of the drug depends on it. Metabolite can sometimes be toxic, inactive, different things can be said. So this is an MS substructure that showed us where OH group is located. However, this OH group cannot be determined in this way, so the MS is cannot help here. So we come to a method. So the position of this OH group can be determined only on the basis of nuclear magnetic resonance. So a more refined structure. This does not seem particularly complicated, but it cannot be done with an MS. And then we can do a combination of LC and NMR. NMR method is very widespread nowadays, and there are devices in various places for all these more refined structural analysis. I will briefly say what an NMR is, and I suppose many of you may not have had an opportunity to see it in practice. So how is the MS different? MS gives molecular weight, and here we get information about different structural parts of molecules, the entire molecule. We can get complete information on it on the basis of NMR. And I would like to say that the compound is put between the poles of a strong magnet, and what's important is that it is possible to do various isotopes that are important, H, C, and F. They all have isotopes that are active and subject to the experiment of NMR. So all of these elements that are of interest to us for organic molecules can be done with NMR. I would like to show you what the aspirin spectrum looks like. So C spectrum and H spectrum were done here. You can see in this first spectrum that all protons can be seen, and here all C's can be seen. And we put this together, we have the full structure, complete structure. And I would like to say how the spectrum is analyzed, and it's a little more difficult to explain on a complicated molecule. The first molecule that was recorded was ethanol, a molecule that is very important and a favorite for the chemicals, and this is how it's analyzed by here we have groups or some patterns. Here we have triplets, singlet, and quadruple. quadruples, and positions of signals in the spectrum are measured. And when we see positions of signals, these are chemically different groups of signals. We have CH2, CH3, and OH. They're located in different positions, and NMR spectrum is defined in such a way. This is a so-called chemical shift. And what enables us quantitative analysis is that below the area of signals, they correspond to the number of protons, 3 for CH3, 2 for CH2, and 1 for OH group. So we have resolved this. It can be quantitative. So the multiplicity of signals points to so the basis of the multiplicity of signals, we can say that this is CH2 or CH3 relative to the oxygen. So why do we need all this? And this is this brief introduction for the NMR. We want to determine the metabolites of buspirone, and we cannot determine where the OH group is. Let's remind ourselves. We did the LC, we got the chromatogram, and we know where this one metabolite is that we cannot, whose structure we cannot precisely determine. And now we have the spectrum of this buspirone, and on the basis, so we are interested in the position of OH group, and on the basis of this spectrum we can determine that OH group is located here. Here it was not completely confirmed. This is the so-called single-dimension spectrum, and we have the so-called two-dimension spectrums or correlated spectrums through connecting. So we can do in two-dimension and connect the C protons through the coupling constants. We can connect parts of the molecule among themselves to each other. We can determine part of the molecule in such a way as presented here. So from this spectrum that seems a little complicated, it is not if you're dealing with this, we managed to determine the position of OH group precisely in the ring. This is very important. The structure of metabolite is very important for explaining the mechanism of the activity of the drug. So this is it. I'm coming close to the end of my presentation. Here it is shown that the analysis is difficult. I keep repeating this, and most modern tools that we have, SP and then HPLC columns, through which HPLC columns, we never have so few peaks in HPLC column, and what we are particularly interested is to get as much data as possible. We always have a UV spectrum when we have HPLC device. We have MS spectrum, we can do MS, and in the end we have NMR spectrum, and in such a way we can compose a structure. I would like you to know that we have instruments that can do this. Here it's an old instrument that was acquired in 1985, and the Ministry of Science was generous enough. We purchased this instrument. It was very expensive, but it was supposed to be used for the anti-doping control. There was supposed to be a basketball championship in Serbia. It's an in this country. It's an enormous device. It could precisely define the mass, but this basketball championship was not held here, but it continued working. Unfortunately, no longer does. We have a very modern device now. It's the so-called SCMS-TOF. It works on the based on atmospheric pressure. It can ionize any molecule at time of life. This cylinder, through this cylinder, ions fly and they go back, and that's how we measure the mass. Here we have nuclear, so NMR device here that costs €500,000. So these are devices that are very expensive. They're very precise though, And if good analysis is done and where nothing can escape, and I would like to end with one slide here. This is a man who is preparing to do an urine analysis. He cannot go out anywhere. He has to drink tons of water in order to clean up, but he doesn't know that there are such precise devices. Despite ton of water he drinks,